In this video, I want to talk through the conclusions we reached from our force of a spring lab. For this lab, our purpose was to determine the relationship between the force of tension in a stretched spring and the amount of spring stretch, how far the length changed. Because we know the farther a spring stretches, the more tension there is in that spring. To determine that relationship, students were given a spring and they had to basically stretch that spring a given amount, as measured in meters, and measure the amount of force of tension in that spring, or stretch the spring so it had a certain amount of tension inside of it and measure how much that spring actually stretched. Once students collected that data, we graphed the stretch values on the x-axis and the force values on the y-axis to determine the graphical relationship between the two variables and the algebraic relationship. Now, to collect that data, each lab group was given a choice. They got to decide how they were going to collect the data, the stretch values, and the force values. To do that, they were given material commonly found in the physics lab, force sensors, mass sets. They had access to all of this stuff, and they had to come up with their own procedure to collect the necessary data. Once each lab group collected their data, they made a force versus stretch graph to determine that graphical relationship, and then walked through writing an equation for that relationship so we could talk about it together as a class. Now, there were lots of different procedures that groups came up with, but they pretty much fell within two different categories. One category of lab procedure involved just stretching a spring horizontally on a table, and it was connected to a force sensor or a force probe, and that force probe was essentially directly measuring the amount of tension in the spring, how much force that spring was pulling on that little hook with. And then students used a meter stick to measure how far that spring was actually stretched for each given force value. Here's one quick example of what a single trial of data would have looked like. The students would have stretched the spring to some length, and the amount of spring stretch is how much the length actually changed. So if the original length of the spring ended here, they stretch it out here, this would have been about 0.28 meters or 28 centimeters of stretch. And for that amount of stretch, for the green spring, the spring was pulling back with about 17.86 newtons of force. Here's another example of what one procedure looked like. A lab group would hang their spring vertically, and then to that they just added different amounts of mass. Well, if they knew the mass that they hung, they could figure out the size of the gravitational force on that mass, and as long as that mass was at rest, then the gravitational force they were exerting by hanging mass was equal to the amount of spring force. And so they knew how much force the spring was exerting, and they could then measure how much did the length of that spring change, how much did it stretch when it had that amount of force. They just hung different masses to give different force values and different stretch values. Groups were either given a green spring, a yellow spring, or a red spring to collect their data. And regardless of whatever procedure they chose, this is kind of a summary of what our final data looked like when we compared it. We all got linear relationships between the force the spring is exerting and the amount of stretch, which we call delta x. And the green springs had a steeper slope, the yellow springs had a slope somewhere in the middle, and any group that had a red spring, their linear relationship had the smallest value slope. And we noticed that our y-intercepts were pretty close to zero, but some of them were over 5% of our biggest y value or the biggest force. So we thought there might be some kind of significance to the y-intercept. We didn't reason it away to be zero. So let's look at an example of an equation from a red spring. The red springs had slopes around 25 newtons for each meter. The green springs were around 50 newtons for each meter, and the yellow springs were around 35 newtons for each meter. Well, our consensus was that the slope was telling us the force required to stretch the spring each and every meter. A higher slope value means it takes more force to stretch the spring for each and every additional amount of stretch. The green springs were harder to stretch, so that makes sense. They had a higher slope value. In physics, we use the term spring constant to mean just this, the force required to stretch the spring for each and every meter. So the slope of our line was the spring constant of your spring. We use the symbol lowercase k to represent the spring constant, and the units are the units of our slope, which are newtons for each and every meter. The y-intercept, our consensus was that it was the amount of force required to get the spring to stretch at all, or to begin stretching. So the y-intercept, we said, was the force required to get the spring to start stretching. The groups who hung the springs vertically noticed that when they just hung the mass hanger on there, just the 50 grams or 0.5 newtons, some of the springs really had no noticeable stretch. And that's because half a newton was not enough force to start the spring stretching. So you had to apply a minimum amount of force, then you would get stretch. In physics, we call that the preload value, the amount of force you have to preload the spring with so that any additional amount of force you actually get stretch. The symbol we use for that is F sub 0, like the initial amount of force needed, and it's a force, so the units are newtons. So the slope and the y-intercept now have names, well, they have meanings, and these are the names that we give them in physics. So here's the general equation for our springs. Remember, we replace the slopes, the numbers in the units for the slope and the y-intercept with symbols which stand for what it represents to give us our general equation. So instead of the slope, we just use k for the spring constant, and instead of the y-intercept, we use F sub 0, which stands for the preload for the y-intercept. So our general equation, at least for our springs, is that the force of tension inside of a spring, or the force a spring will exert, is equal to the spring constant of the spring times its stretch in meters plus any preload value. Now, our springs, most of our springs had some amount of preload value. It required some force to get it to start stretching. Well, not all springs actually have preload values. And if we had springs that had no preload values and yet there was a linear relationship between force and stretch, like these would be two examples of linear relationships between force and stretch for springs with no preload value, there is no y-intercept, we would call those ideal springs. And that's the term we use in physics for a spring that has a linear relationship between force and stretch and has no preload value. From this point on in class, we're going to assume that all springs are ideal. So there is no preload value, and there is a linear relationship between the two variables, the force and the stretch. So that means our general equation, if there's no y-intercept, just turns into this. It's the force a spring exerts is equal to its spring constant times its stretch. And we just use stretchy springs, but this also applies to ideal compression springs. So this would be how much the spring, gets smaller from its relaxed position rather than gets longer. So it could refer to its compression or its stretch. And this is actually known as Hooke's law. This only applies to ideal springs. If you're in AP Physics 1, if you look on your AP Physics 1 equation sheet, you'll find something that looks like this, but a little bit different. So here's what it looks like with the notation. There's just absolute value signs for the force, the size of the spring force, and the amount of stretch. And they don't use a delta x to represent the stretch, they just use x. So this says the size of the force a spring exerts will be equal to its spring constant times the amount of either stretch or compression. So at this point, for writing your lab report, this is as far as you need to go. We do have 3 new terms you need to define: spring constant, preload, and ideal springs. Now I just want to end the video with one last thing related to ideal springs. One AP Physics 1 question I've seen before sounds something like this. They say, how would you determine if a particular kind of spring acts like an ideal spring? So let's say a rubber band. Is a rubber band considered an ideal spring? Does it have a linear relationship between force and stretch and no preload value? Well, you actually have to determine that experimentally. So here's a picture of an experimental setup I used to try to answer that question. Does a rubber band behave like an ideal spring? Well, you'd have to go through and collect force values and stretch values and make that graph of force versus stretch to find out, is it linear and does it have a preload value? So I just connected a force sensor to a rubber band directly to measure the size of the force, and to get the amount of stretch, I actually used a motion detector, which was measuring the location or the change in position of this low friction car, which was attached to our sensor, which was attached to a rubber band. I zeroed it so that when the rubber band was relaxed, this was a 0 position, and when I moved the car backwards, the change in position of the car was the same as the amount of stretch of the rubber band. So I just pulled the car back slowly over 10 seconds, and the rubber band pulled with as little as 0 newtons of force all the way up to a little bit below 20 newtons of force. and it stretched, from no stretch to about 30 centimeters or 0.3 meters of stretch. So I had two graphs, force versus time, position versus time, or this would be stretch versus time. And if you look at the same time, like let's say at 2 seconds, the rubber band was stretched 10 centimeters and was pulling with 5 newtons. At 4 seconds, it was stretched about 0.2 meters or 20 centimeters and was pulling with, a little over 10 newtons of force. Well, I had all of those values collected, the force values and the position values, and then I just took each force in each position at the same time and plotted force versus position. This is what that looked like. Now we can answer the question. Does a rubber band behave like an ideal spring? Well, what does an ideal spring behave like? Well, it needs to have a linear relationship between force and stretch. That is clearly not linear, so it is not ideal. It also, any amount of force I applied did stretch the rubber band, and so there was a negligible preload value, but it's not ideal because it's not linear. Right? Like if you look when it's stretched about 10 centimeters or 0.1 meters, the slope of our force versus stretch graph is, remember, the spring constant. Well, this thing doesn't have a spring constant because its slope is changing. Initially, the steepness around 10 centimeters of stretch is 35 newtons for each meter. That's about the stiffness or strength of the yellow spring. But when I got closer to 0.3 meters of stretch, see the steepness of this is around 130 newtons per meter. That's way stronger, over twice as strong, twice the spring strength as our strongest spring, the green spring. So a rubber band does not behave like an ideal spring.